Hi guys, welcome back to my channel. So in my previous video I went over supervised learning, unsupervised learning and reinforcement learning, and I did like a rough overview of these three. And if you guys haven't watched that video, the link to that in the I button, make sure to click on that and watch that video. Alright, so let's continue with this one, which is like a full depth video on supervised learning. So let's get started. So first, in the supervised learning, we start with a training set. That contains pairs of inputs and outputs. So the inputs here are basically x1, x2, x to the n that you see, and the outputs are y1, y2, yn. Okay, and these outputs are generated by some unknown function f. So in other words, there's a real world rule that maps inputs to outputs, but we don't know it directly. So that's where the role of hypothesis comes in. Our goal is to approximate this unknown function f using the function called h, the hypothesis. So h is basically our model, our best guess about how the world works. We choose h from a large set of possible functions, okay, which we call the hypothesis space. So essentially, supervised learning is the process of finding the best hypothesis that maps inputs to the outputs. Okay, so the x all the inputs and the y is all the outputs. Okay, so that's basically supervised learning. So let's move on to consistent versus best fit hypothesis. So our hypothesis h is called consistent if it perfectly matches the training data. Okay, so that means for every xi, the input xi, okay, there our hypothesis predicts exactly one yi, the output yi. Okay, so but here's the catch. In real life, the data can be messy, okay? It can be noisy or it can be incomplete. So instead of a perfect consistent function, what we really want is a best fit function, okay? Something that makes prediction that are close enough to the true outputs, okay? So the true measure of a good hypothesis isn't just how well it fits the training data. It is basically how well it performs on the new unseen data. Okay, the ability, so basically this ability to make accurate predictions on the data it has not seen before. This is the concept of generalization. Okay, so generalization basically mean we do not want the machine to memorize the data. We instead want it to generalize it. So so like generalizing it, so it is able to predict predict clearly on the unseen data. Okay, so if our hypothesis h generalizes well, it can make prediction on the outputs for new inputs almost as accurately as it did for the training examples. Okay, so let me explain this concept of generalization with an example so it makes more sense. Okay, so imagine we're training a model to predict the housing prices. Okay, so our input x in this case would be the size of the house, and the input y in this case would be the price of the house. Okay, so the true function f is complicated and unknown over here, but our job is to come up with a hypothesis h, like a line or a curve that approximate well this relationship. Okay, so what we did is like we made a graph for the housing and for the house size and the price of the house. Okay, and it kind of looked like a scattered plot, right? You guys see the training data that in the yellow, so it's like a scattered plot, and just by looking at it we can pretty much figure out that the best fit for this function is a linear function, right? It just best fits the training data. Okay, so this is basically our hypothesis, and you guys see in the green we are making prediction on the size of the house, and we're making a prediction for the price. So the first one is 62,000 and the second one is 97 and so on. Okay, so we're making a prediction on the unseen data, and which is very good and close to the training data that you see, right? So it is a good one. So this is basically what it means by generalization. So it is able to come up, with good predictions, and because the model it just didn't memorize the data, the training data, it has just generalized it. So that's why it's able to make prediction very well. So if our hypothesis generalizes well, it won't just fit the training house, it will also correctly predict the prices for new houses which it has not seen before, and that is the core concept of generalization. Okay, so let's go a little deeper into supervised learning by talking about the hypothesis and the hypothesis space. So first, the function that we are trying to learn, the one that maps the input to the output, we call it the hypothesis space. Okay, and basically our hypothesis is just a model's guess for how the input relates to the output. Okay, just like how we were guessing the linear line in the function of the housing prices, right? So that was our hypothesis. But where do these hypotheses come from? They don't just come up from in the air, right? They're drawn from what we call a hypothesis space. This is simply the set of all possible functions we're willing to consider. Okay, so let me give you some examples to make this clear. Okay, so imagine our hypothesis space is the set of all polynomials of degree 3. Okay, so that means our model is restricted to only choosing functions that look like cubic functions. Okay, the cubic function that you see on the screen. So another example could be like maybe our hypothesis space is the all set of JavaScript functions, okay, or our hypothesis space is all set of decision trees, or it could be all linear functions. Okay, so there can be a lot of possibilities, but the important point here is that we define this space beforehand, okay, and our algorithm then searches within this space for the best possible hypothesis. Now, in different vocabularies, instead of saying hypothesis, we often say this model. Okay, so we can describe this as H is a model of the data chosen from a model class H. Okay, so in the other words, H is just one specific function that we pick out of a large family of function. Okay, and finally, whenever we train the true output, we're trying to predict for each input the actual correct label or the answer. We call it the ground truth. Okay, so this is what the real world gives us, and what we want our hypothesis is to approximate as closely as possible. Okay, we understand what a hypothesis space is, right? So the big question is, how do we actually choose one? Okay, so well, there are few strategies we can use. First, sometimes we already have the prior knowledge about the process that generated the data. For example, if you're modeling population growth, okay, we might come up from biology that the population growth often follows a logistic curve, right? That is a prior knowledge that we have. So that prior knowledge immediately gives us a hint about the kind of the function, right? Or the hypothesis space that we should consider. Like this prior knowledge, it is giving us a hint that if it's population growth, so that it's gonna be logistic curve. So so that we can come up with a hypothesis space, right? But if we don't know any strong prior knowledge, so this is where EDA comes in. So EDA means explanatory data analysis. Okay, so this means EDA, which basically means carefully examining the data before we build a model. Okay, so what we are gonna do is like we're gonna go through a statistical test, and more importantly through visualization. So like we will make histogram, scatter plot, box plot. So we'll try to come up with ways to visualize the data. Okay, so for instance, if we make a scatter plot of housing and the pricing, okay, so just like how we did in the example that I showed you, so it looked like roughly a straight line, right? We could see it just by plotting it, right? So that was a step of EDA as well. We were visualizing the data. Okay, we could see that the linear function is a good starting point for our hypothesis space in that example of the housing prices, right? So if the data is clearly curved or it shows more complexity, we might need polynomials, we might need decision trees or neural networks. So EDA is basically giving us the initial sense of what might work. Okay, so finally there's the practical approach. If we're unsure, we can just try multiple hypothesis space and compare them. Okay, so like we're not sure what to do, so we can basically try multiple things. So for example, we might train a model, train with a linear model, okay, or we might train with a polynomial model or a decision tree, and then we can evaluate which one gives the best performance on the unseen data, because our goal is basically to be able to predict on unseen data, right? So that's why we choose different models and we try to see the best performance on the unseen data. Okay, this is a very common strategy in machine learning, experimenting with different models and then selecting the one that balances accuracy and generalization. So in short, we're going to use like prior knowledge if we have it, and we're going to use EDA, the EDA explanatory data analysis, which is basically mean visualization, okay, to guide our choice, or we can test multiple hypothesis space and see which one works. Okay, so that this is basically how we choose the hypothesis space. All right, so let's look at very important concept in supervised learning, how different hypotheses fit the same data. Okay, so on the screen that you see over here, we see two rows of plots. The top row shows 4 different models trained on the same data set. Okay, so they're basically trained on the same data set. Okay, so the data set 1, which is the top row that you see over here, each column corresponds to a different hypothesis space. Okay, so the first one we took the hypothesis as a linear, the second one sinusoidal, and the third one piecewise, and the fourth one as a 12-degree polynomial. Okay, so these are the same data sets, but we choose a different hypothesis space for each one of them and see that it performs well on which one. Okay, so you know, on the far left we have a linear model, okay, which tries to fit the data with a straight line, and next we have a sinusoidal function which tries to fit the data with a wave line, and then we have a piecewise function which breaks the data into segments and fits a line to each piece. Okay, and finally on the far right we have a 12-degree polynomial, which is a very flexible function capable of creating lots of wiggles and bends. Notice what's happening here. Even though all these models are trying to fit the same data, the way it fits, it's completely different depending on the hypothesis space we choose. Now let's move on to the bottom row. Here the same 4 models are used again, but this time training on a slightly different data set, okay, called the data set 2. Okay, this data was sampled from the same underlying function but just with different points. Okay, so the important thing that you guys notice over here, the linear and the piecewise function looks very stable. Okay, here they don't change much when the data changes slightly. Okay, so we just made a change to the data and you guys observe which one basically performs on the changes. Okay, so basically we came up that the linear and the piecewise look stable here, but you know, the high degree polynomials, they go wild. Okay, small changes in the data lead to big swings and fitted curve. You guys see the 12 polynomial, it just has a lot of swings over here. Okay, this is a clear example of overfitting. So what we did over here with the high degree polynomial, we overfitted the data. Okay, where a model, so overfitting is where a model is too flexible and tries to fit every little noise in the data instead of capturing the true underlying trend. Okay, I'll go over overfitting later in this video in more depth. Okay, so what is the takeaway from this slide over here? So it is basically that the choice of the hypothesis space, it's going to dramatically affect the kind of function we learn. Okay, so basically simple models like linear or the piecewise functions might not fit the data perfectly, okay, but they generalize well when we get new data. Okay, so and more complex models like high degree polynomials can overfit. They look like they fit the training well, but they're gonna fail to generalize. Okay, so this balance between simplicity and flexibility is the heart of supervised learning. We want a model that captures the main pattern, but it doesn't chase every little noise in the data. Okay, so let's move on to supervised learning, the bias variance trade-off. Okay, so so this is like the most important concept in supervised learning, the bias variance trade-off. The idea is basically which helps us understand why some models perform better than others. We start with bias. Bias is the tendency of a predicted hypothesis to deviate from the true expected output. Okay, so in the simple words, bias is the error that comes from making assumptions about the data. Okay, so bias is the systematic tendency of a predicted model to deviate from the expected function across different training sets. Okay, so in the image, the true function is non-linear. Okay, so it's like a curve sinusoidal function, right? But our hypothesis space, you guys see, it is restricted to only linear function. So the model cannot capture the true shape. This restriction forces the model to fit in a biased way, producing prediction that systematically miss the true curve. Okay, so what's the takeaway over here? So it is basically bias arises from restrictions. Okay, if the hypothesis space is too simple, like using only lines for a wavy function, this model will consistently deviate from reality, no matter how much data it sees. Which means with lots of data, with lots of training data, a biased model cannot fully approximate the true functions. Okay. Now, when the bias is too high, our model fails to capture the pattern in the data, which is called underfitting. Okay, so imagine trying to fit a straight line to the data when there's clearly curved. Okay, so the line just won't capture the trend, right? No matter how much hard you try, right? So just like how you guys can see in the picture over here, so the black dots that you see over here are the training data. Okay, so which is basically generating a curve that you see over here. So it is quadratic. It is generating a curve with the training data that you see over here, right? And the green curve, which is quadratic, and the red that you see over here, the red line, is basically the model's prediction, which is linear. Okay, and why do we call this an example of underfitting? This is because the true relationship between x and y is non-linear, and we can clearly see it, right? It is non-linear, it is quadratic. However, the model is making it linear. So that's why we consider it overfitting. The model is too simple over here. It's not allowed to fit a straight line. As a result, a line misses the curvature of the real function. Even like with more data, the model cannot improve because its hypothesis space is too restricted. Okay, so the key takeaway over here is that underfitting happens when the model is not complex enough to capture the underlying trend in the data. So it's gonna lead to high bias, systematic errors, and it's also gonna lead to poor performance on both the training data and the testing data. Okay, so on the other side, we have variance. So variance is how much our hypothesis changes when we train or on a slightly different data set. Okay, so that means like a high variance model is extremely sensitive to a small fluctuations in the data set. Okay, so this leads to overfitting. Okay, so overfitting basically happens when the models pays too much attention to the training data set. Okay, so even like memorizing the tiny details or the noises. Okay, and as a result, it performs really well on the training data. Okay, but it's going to perform very poorly on unseen data. Okay, so overfitting performs well on the training set but performs very poorly on the unseen data. Okay, so here in the example that you see over here, the true function is quadratic. Okay, so the green true function with the black dots, the training set that you see over here, it is a curve, right? So the model used is an overly fitted 15-degree polynomial. Okay, so here the actual one is the curve, but the model, the hypothesis that we use is a 15-degree polynomial, which is basically overfitting it. It is like fitting every little noise of it, every data set of it. It is fitting the training set very well, but it's gonna, when we try to make predictions of it, it's gonna poorly make predictions of them, right? Because it's like the shape of it, it's not good. So here in this case, a curve looks is going to fit the data set very well. Okay, so this is an example of overfitting. It fits the training set data almost perfectly, even the noises, but it deviates widely from the true underlying trend. The way over here is that overfitting happens when the model is too complex relative to the underlying data pattern. It leads to low training errors, high test errors. Okay, so it's going to fail to generalize on new data set. Okay, and to summarize, the art of supervised learning is finding the right balance between bias and variance. Okay, so our goal is basically to come up with a hypothesis that is just like complex enough to capture the underlying pattern, but not so complex that it memorizes the noise as well. Okay, so in other words, we want to minimize both the underfitting and overfitting and come up with a hypothesis that perfectly matches the data set. Okay, so that was it for today's video. I'll go over Bayes theorem in the next video, and make sure to subscribe so you get a notification for that video. Okay, so that was it. Bye.